With our standard normal distribution, we've been concerned more with how individual data values vary about the mean. Statisticians, though, are also interested in knowing how means of samples, because again, we take a lot of samples in statistics, and if we can take the mean of those samples, how does that compare to the mean of the population? So let's say, for example, researchers took a sample of 30 adult males, and they wanted to find their triglyceride levels, and they came up with like 187 milliliters per deciliter. And then they took another sample of 30 males and found their triglyceride level to be 192, the mean. And they kept doing that, and they did it for like 100 samples, and they got 187, 192, 184, and so on. So they had a bunch of different sample means. And I'm saying triglyceride levels, but it really could be anything. How does the mean of these samples compare to our population mean? So a sampling distribution of a sample means, it's a distribution using the means computed from all possible random samples of a specific size. Okay, so we're doing the means of samples of basically the same size, and this was up here 30 males, adult males. So this is our sampling, okay, all these numbers. Now, if you can do that with replacement, meaning, again, people get thrown back in the pot, they could get chosen again, your sample mean is going to be different from your population mean. And that's a sampling error. Now, sampling error is going to be the difference between the sample measure and the corresponding population measure. What you need to take away from it as our sampling error is because the sample is not a perfect representation of the population. So how do we get around there? Okay, we're going to take 30 males and we're going to test their triglyceride levels, and we're going to take 30 different males, or maybe some are repeated, and we're going to take the mean of their triglyceride levels. I don't know why I can't say that, I apologize. And we're going to keep coming up with these different means. Well, if you had the entire population, how do we get these? How do we compare? Because it really isn't going to be possible always to get the population mean. So when we're talking about sample means, just stick with me here for a second. The mean of the sample means will be the same as the population mean. So before, okay, the sampling error is not perfect representation. We know that these means are going to be different from the population mean. So if we take the mean of these means, the average of the averages, that's going to be the same as population mean. Now the standard deviation will be smaller than the standard deviation of the population. The standard deviation of the sample means, the average of all the means, is going to be smaller than the population, but it's going to be equal to the population standard deviation divided by the square root of the sample size. Let's come back to that. Let me just show you a little example, and really I just want to talk to you about what's leading up to the central limit theorem. Let's say a professor, to make things easy, gave a quiz, an 8-point quiz, and he gave it to 4 students. And the first student scored 2, second scored 6, 4, and 8. Okay, so all we're doing here is we're saying these are quiz scores. All right, so this is our population. We have 4 students. This is their quiz score. One got 2, 6, 4, and 8. So if we were to find the mean, there's that mu symbol again, the population mean. Add them all up, divide by the 4, we get 5. So our mean score is 5. Now if we want to do our standard deviation, okay, remember, and I might be missing some information here. If we want to do our standard deviation, and let me just calculate it, we have our variance here. And I'll just leave it for now. But anyway, if you use the old formula, okay, and you find your variance, you get 2.236. Anyway, we'll come back to that. If you look here, if we were to do a frequency of our 4 quiz scores, who scored 2? One student did. Who scored 4? One student did. Who scored 6? One student. Who scored 8? One student. So it doesn't really look like a standard normal distribution. It's called a uniform distribution. But let's say, remember now we want to do, the mean of the sample means. Okay, stick with me. Promise it'll get easier when we get to the formula part. We're using the same information here, but let's say we're taking a sample of size 2. Remember, it's a specific size. Okay, so we're going to take a sample, and we're going to say, out of our 4 students, we took a sample of 2, and they both scored 2. So obviously their average is 2. And then we took a sample of 2 students, and one scored 2 and one scored 4. Their average is 3. 2 students, one scored 2, one scored 6. Average is 4. All the way through all of our possible samplings that we could take at 2 students. Then we can create a frequency distribution. So 2, 3, 4, 5, 6, 7, 8. Okay, we get our frequencies here. 1 had the 2 right here. There was 2 that had a mean of 3, this one and this one. There was 3 that had a mean of 4, 1, 2, 3. There was 4 that had a mean of 5. You kind of get the idea. Now, if you were to graph it, this kind of goes along right here with our histogram. We're going to say 1 student scored 2, 2 students scored 3, 3 scored 4. We get this nice normal curve. But here's the thing. If we were to take the mean of these sample means, again, here's all our samples. There's the mean of each sample. If we were to find the mean of that mean, we get 5. Remember, our population mean with just 4 students was 5. So that's why they're saying the mean of the sample means will be the same as the population mean. Okay, again, just kind of stick with me. The standard deviation then, and this is where I need to go back here. The standard deviation, remember, is going to be the same. Excuse me for 1 second. Sorry about that. But it gave me a second to figure out that back here, whoops, this is the standard deviation. It's not the variance, and it's because the square root sign's right here. Anyway, so this is our standard deviation of our population. That's when we had the 4 students. We've seen now that if we do the sample mean of our sample, we get the same mean. Now let's talk standard deviation. If you go through our standard deviation formula, again, you're subtracting off the mean and squaring it of each of the values and the frequencies here, and then take the square root, we get 1.518, which is not the same as our original. But remember, it's going to be equal, the standard deviation is going to be smaller, but it'll be equal to the population standard deviation divided by the square root of the sample size. Divided by the square root of the sample size. Notice the 16 right here. 1, 2, 3, 4, 5, 6, 7, 8. There's 16 samples. So if you take that standard deviation and you divide it by the square root of the sample size, okay, so you take 2.236, that was our standard deviation, and we divide it by the square root of the population, and in this case, 2. Well, it was 2 because we took a sampling of 2. We get the same answer. Okay, what's all this leading to? Because I know your head's probably spinning right now, and that's okay, -2. The standard deviation of the sample mean is called the standard error of the mean. How far off are we? So, our standard deviation of the sample mean, that's this x with a line over here, is the standard deviation divided by the square root of the number of factors. So, I'm sorry, it's square root of the sample size. That leads us all to our central limit theorem. Whew. Okay, as our sample size increases without limit, the shape of the distribution of the sample means taken with replacement will form a population with mean u, and a standard deviation will approach a normal distribution. Why is that important? If it's normal distribution, we can use those charts and we can get those areas or those probabilities. This distribution will have a mean, mu, and a standard deviation of whatever the standard deviation divided by the square root of the sample size. Okay, square root of the sample size. Okay, here's our new z-score or z-value formula. All of that is going to lead to this. Notice you really, hopefully, haven't written down too much. This is what it's getting at. We're going to have a new z-value formula. You're going to take the mean of the sample. This x here is going to be the sample mean. This mu thing here, remember, that's our population mean. The denominator here of standard deviation divided by the square root of the sample size. That's the standard deviation of the sample means. So, and we'll talk about later what z-value score we use. For what we're going to do right now, though, this is our z-value. This is how we're going to find our z-value. So, when you use our central limit theorem, that's kind of the central limit, which leads to the z-value. When the original variable is normally distributed, the distribution of the sample means will be normally distributed. That's key. We wanted that normal distribution. If it's not normal, a sample size of 30 or more is needed to use a normal distribution to approximate the distribution. Basically, the larger the sample, the better the approximation will be. Okay? So here is our population mean, and then we're going to have one sampling error on either side. Whew, lots of talking, a lot of variables, a lot of different things, but basically this is what it boils down to. We're taking samples we're taking samples and then we're taking the mean of those samples. Sampling distribution of a sample means. When the population's too big, we take samples. We're going to take the means, the averages of those samples, and then take the average of that. Going through all that, we can still use our standard normal distribution if the original variable is normally distributed using this new z-score formula, which you're going to see really isn't as scary as it sounds when we get into some examples.